Hi, and welcome to this session where we'll take a look at the General Footing module within the Structural Engineering Library. The first thing that we'll take a look at is how we can add a general footing calculation to an existing project file. So I have an empty project file created here. I've clicked on the calculations item in the project manager, and then I'll come up and click on the add button. And then over here in the foundation category, it's the top item, general footing, that we're looking at here in this video. So I'll click general footing, and now we can see that the graphical user interface has updated itself to reflect the general footing module, and we see the tabs ready to collect the input for this calculation. Notice that the screen is generally broken up into an upper portion where we have our input data fields, and we will work through each of these tabs in succession to see what all of them are used for. And then we have a lower portion of the screen, which is typically where the results are displayed, and we'll also work through all of the available results tabs so that we can see everything that the program offers to us once we complete our calculation. So we'll begin our tour of the general footing module by starting here on the tab named General. And the very first item that we come to is a free-form description. So this might be something like footing at B1, for instance. Moving down the screen, we have a category called Material Properties that collects information like F'C for the footing, Fy for the rebar to be used in the design, the Young's modulus for the concrete, the unit weight of the concrete, and then phi values for flexure and for shear. All of those values look good to me for our example, so I'll just leave those as is. And we'll come over to the right-hand side of the General tab, where we have a category named Analysis and Design Settings. The first thing that we come to in this category is a couple of options to consider the footing weight when determining the soil bearing pressure, and the option to consider the footing weight when determining sliding, overturning, and uplift results. For our exercise, I'll leave both of these options selected, but I just wanted to point out that they are there and available for you. So if you have a specific reason to want to exclude the footing weight in one or both of those checks, you have the ability to do that with those checkboxes. On a related note, if you happen to have a specific situation where you know that a footing is precluded from sliding for some reason, maybe there are grade beams framing in from both directions or some other sort of detail, you can communicate that to the program by checking this option that says ignore checks for sliding. In our situation, I don't want to select that one. I'd like to see some results for the sliding check, so I'll leave it deselected. Moving down, we have a couple different options for specifying minimum steel ratios. There's an item here where you have the option, if you so choose, to provide a ratio that will be used for a minimum steel value, and this one, as indicated, will be based on the D dimension, in other words, the footing thickness minus the calculated clear cover at the bottom. The other item is one that is specifically keyed into the ratios that are provided in the current code for temperature and shrinkage, and it will be based on the entire thickness of the footing. So for our purposes, I'm just going to change this upper one to a value of 0. I don't have any specific reason why I would want to limit the reinforcing on the basis of the D dimension, but I do want to make sure that, as per code, the temperature and shrinkage minimum ratio of 0.0018 is respected in the design. I'll skip the factors of safety for just a second and come down to this last checkbox called Consider ACI 10.5.1 and 10.5.3 for minimum reinforcing. This is provided as an option for some specific instances where a user may want to hold to those particular values as minimum reinforcing for a footing. It's generally understood now that this is not applicable to footings So it is created as an option in case you happen to have a footing where you want to hold this more stringent reinforcing criteria. But for our exercise, I will definitely leave that one deselected. Back up to the factors of safety. These two spinners allow us to set the minimum overturning factor of safety that will be deemed acceptable in the design, and then the minimum sliding safety factor that will be acceptable for our design. And I'll leave both of those set to values of 1.0. So that's a full look at everything that we have on the General tab. The next thing we'll do is take a look at the Soil Allowables tab. So here on the Soil Allowables tab, the first category that we come to is called Soil Design Values, and the first item in that category is the allowable soil bearing pressure. So what I'd like to do is just set this to a value of 4 KSF for our example. I would just point out that there's a convenient table here that you can open with this icon that points you directly to the prescriptive values in the code. So if you choose, you can reference that. The next item down is an option to increase the bearing value by the footing weight. So if you choose to do that, you can toggle the yes button. In our case, I'll just leave it set to no. The next item down is called Soil Passive Sliding Resistance, and the note beneath it tells us that this will use the entry that is actually over here on the right hand side of this screen called footing base depth below soil surface. So this value that we can enter for passive pressure will be multiplied by whatever footing base depth we ultimately specify here to calculate a passive force. Finally, we have the coefficient of soil concrete friction, where we can enter the appropriate value. So I'll leave both of these at their present values, 250 pounds per cubic foot for the passive sliding resistance, and I'll leave the coefficient of friction at 0.3. Now moving over to the right hand side of the Soil Allowables tab, we have a category called Soil Bearing Increase. Now this first item, footing base depth below soil surface, plays a little bit of a double role. We saw that it will be used over here in calculating a passive resistance if we choose to use that. So that's one of the functions of this value. I'll enter a value of 4 feet. The other thing that it does, though, is it relates to these items down below where we can prescriptively apply increases in the allowable bearing pressure that we specified over here a couple different ways. We can prescribe increases that are based on the footing depth, where we can say that the allowable pressure increase per foot is, say, 0.25 KSF when the footing base is below, and we might say below 3 feet, for instance. Now as I make changes here, we can look down to the bottom and see the adjusted allowable soil bearing. So we can see that as compared to my specified value of 4 KSF over here, we've already received a little benefit because we're at a 4-foot depth and we've allowed ourselves some increase per foot below 3 feet. One of the other options would be to specify an increase in the allowable soil bearing pressure on the basis of the footing plan dimensions. So we could also say that there's an allowable bearing pressure increase of perhaps 0.15 KSF when the maximum length or width is greater than, and we might specify some footing dimension here. Now, this change won't reflect immediately for our situation because we're jumping ahead just a little bit, but we haven't yet specified the footing size. So this would get adjusted as we start to provide a meaningful footing size, and we would start to take advantage of this benefit as well. I'll just leave these values in here. They're not based on anything real, but we'll just leave them set as is for now. The other thing that I would point out is that you do have the ability to set an upper limit or an absolute maximum allowed bearing pressure so that these things can't accumulate to something that is greater than some safe value. So for instance, that might take on a value of 8 KSF, we'll say. And that would just see to it that this adjusted allowable soil bearing never exceeds the 8 PSF. The node indicates that a value of 0 would be considered as no limit whatsoever. So if you wanted to just let these things go as high as they can, you could just enter a value of 0 here for the maximum allowed bearing pressure, and this adjusted allowable soil bearing would just turn out to be whatever is calculated based on these values up above. Okay, so that is a complete look at everything here on the Soil Allowables tab. The next thing that we'll do is move on to the Footing Size and Reinforcing tab. On the Footing Size and Reinforcing tab, we have two sub-tabs that we can start working with. The first one is called Dimensions, and on the Dimensions tab is where we can establish the dimension for the width of the footing and for the length of the footing using these spinner arrows. Now, I want to take a minute to move over to the diagram here and just point out that width and length have some physical meaning with respect to the coordinate axes that are used later to apply loads to this footing. So note that the width is parallel to the x-axis, and on the diagram we can see that this is the width dimension and that it is in fact parallel to the x-axis. And then likewise, what we refer to as the length of the footing is parallel to the z-axis, and we can see that the z-axis runs up and down the screen, as does the length. So that all coordinates. And then the other layer that's important to understand is that we've named the four edges of the footing. So notice that there is a reference to the top of the footing and the bottom of the footing, not to be thought of through the thickness of the footing, but to be thought of in a plan dimension sense. So the positive z-axis protrudes through the edge that's referred to as the top. The negative z-axis pops through the edge that's referred to as the bottom. And then when we look at the edges to the left and right, we just use those terms. So the left is the negative x-axis and the right is the side that the positive x-axis protrudes through. So for now, what I've done is I've just started with some values in here. I'm not really sure what it's going to take. In fact, I'm just going to make up some loads when we get to the Applied Loads tab. But I'll just set values of 3 feet by 3 feet for the plan dimension. Notice that the footing thickness is also specified here and that it is specified in units of inches. Now, while we're talking about dimensions, I'd also like to point out that there's a button here, Auto Calculate Footing Size and Thickness. If we go the rest of the way through the tabs and apply loads and define load combinations, then we might want to come back to this button and give it a click and see that the program has the ability to optimize the footing plan dimensions and to some extent the footing thickness for us, which will be a big time saver in terms of trying to get to a correct size. So if that's your mode of operation, then keep in mind that the program can help you in that regard with this button. Since I don't have loads applied yet, it won't be meaningful to click this button at this point in time. Continuing down through the list of input here on the Dimensions subtab, notice that there is a load location offset from the footing center and that the note says one axis only. These two buttons allow us to decide whether we would like to specify a load offset from the footing center line to the center line of application of the loads, and if so, we have to identify whether we want to shift it along the x-axis or if we want to shift it along the z-axis. At the present time, the module does not have the ability to handle both an x and a z shift, so if we have a shift at all, it will only be about one axis, and we need to just select which axis we want to shift parallel to and then provide the distance that we want to make the shift. For our exercise, I'll just leave the pedestal or the footing concentric, the point load concentric with the center line of the footing by leaving the value set to 0 for the load location offset. The next pieces of input are the pedestal dimensions. We collect a dimension parallel to the x-axis and a dimension parallel to the z-axis, and we collect a pedestal height. Now these are important for a couple reasons. Number one, they define the location where the moment will be calculated, and for that matter where the one-way and punching shear checks will be conducted as well. But they also define the size of the pedestal, which when used with the unit weight of concrete will define an additional load that we can apply to the footing in the form of the self-weight of the pedestal. So for our exercise, what I'm going to do is define a 24 inch by 24 inch by, we'll say, 36 inch tall pedestal. The last decisions that we have to make here on this tab are whether or not to consider the pedestal weight when determining the soil bearing pressure and or when determining the checks for sliding, overturning, and uplift. For our exercise, I'll select both of those so that the program uses the weight of the pedestal based on these dimensions and the unit weight we specified when it checks soil bearing pressure, sliding, overturning, and uplift. Okay, that's a full look at everything on the dimensions sub-tab. I'd like to move over to the reinforcing tab to point out that this is the location where we will identify the number of bars parallel to the x-axis and the size of those bars, and then the number and size of bars parallel to the z-axis, and we'll identify the dimension from the rebar center, and note this is a dimension to the center from the edge of concrete at the bottom surface. So if you're normally used to specifying 3 inches of clear cover at the bottom, you're going to want to allow for the dimension of half the diameter of your bar. So perhaps you might say something like 3 1/4 or 3 1/2 inches in this input. Now we'll come back and revisit the reinforcing layout after we've applied some loads. So for now, what I'm going to do is I'm just going to say that I want to use 6 number 6 bars in each direction, just so we can see how those controls work. But we'll definitely need to refine that and optimize that once we get loads and load combinations defined. I would also point out that there's a convenient rebar list here that this icon launches, where you can open up this little table that shows you the total area that's provided by some number of a certain size of bar. So this may be convenient for you to use if you're looking to achieve a certain area. And then notice that the table is configurable, so you can select the starting bar size and the ending bar size, and then the maximum number of bars to include in the sets, and sort of customize this little dialog as you see fit. And then there's even an option to select this number and size of bars if you wanted to do that. So there would be 6 number 7 bars from that table. Okay, the last thing that we want to touch base on with the reinforcing tab is this bandwidth distribution check down at the bottom. The referenced section is indicated here, and this is only something that's applicable to rectangular footings. So since we've defined a square footing, we won't see anything meaningful until I tick that up by 1 so that we have something that's somewhat rectangular, and then we start to see values that are reported here. So this is just performing that simple check that reports the bandwidth and then the percentage of reinforcing that's required to be within the zone and the percentage of reinforcing that's required to be outside of that zone. I'll just reset this back to a square footing for now and come back to the reinforcing tab to show that when the footing is square, those are all nulled out as being not applicable. That's a thorough look at everything that we have available to us on the footing size and reinforcing tab. We'll certainly come back and revisit this tab again after we apply loads and we look to refine our reinforced concrete design, but for now we'll move on to the Applied Loads tab. The Applied Loads tab is the tab that we'll use to assign all of our applied loads to the footing that we're currently studying. Let's just take a quick spin around and get familiar with the different options that are available on this tab, and then we'll key in some numerical values. First, notice that there are three tabs here, sub-tabs. One is for vertical loads, one is for moments, and the other is for shears. Notice that the note reminds us that in these three tabs we're entering unfactored loads, in other words service level loads, because we're going to take care of factoring and combining on the load combinations tab. We have a note that reminds us that we can specify the pedestal position on the footing size and reinforcing tab. And then the graphic reminds us that positive shears will act toward the positive Z or positive X edge of the footing. Positive axial loads will be considered downward because the majority of our loads will be gravity loads. So in order to save a lot of negative signs, we just declare that positive values will be considered downward. Some of this is echoed for us down here in the form of notes as well. The P loads, which are along the y-axis, are considered to be gravity loads, so their positive values are considered to be acting downward. Specific to this vertical loads tab, notice that there's also an overburden input area where we can specify an overburden load. It too is considered to be a downward acting load when positive, and it represents a uniform load over the footing area, but it will not be applied in the area that's covered by the pedestal. So keep that in mind. If you're trying to check something very closely, just remember that your specified overburden loads will be omitted in the small area that is covered by, or whatever area is covered by, the pedestal. I'm just going to click to the Moments tab here to show that the moment sign convention is also displayed for us both here, and it's written out in text down here. It tells us that positive moments create higher soil pressure at the positive X and or positive Z edges of the footing. And then the other important thing to understand about this module is that, as we mentioned before, with regard to the shifting of the pedestal, the module does not consider biaxial loading in its present situation. What it does consider is uniaxial loading, and it is set up to allow us to look at uniaxial loading about both axes within one run, but it's important to understand that these are not superimposed in any way. So that's the meaning of this note here, which says that moments are not applied about the axes simultaneously. So when we get down into the results section, we will see moments about the x-axis and moments about the z-axis. It's just important to understand that these are parallel analyses that are being run and parallel sets of results that are being reported, but they are not being combined or superimposed, and they do not interact in any way. Along similar lines, if I come to the Shears tab, this also reminds us of the sign convention for shears. So positive values will create higher soil pressures at the positive X or positive Z edges of the footing. It tells us that the shear is considered to be applied at the top of the pedestal. So again, an important item to note because that directly affects the moment that will result. And a note that also reminds us of the fact that shear will cause both overturning and sliding, because sliding, fairly obvious, the overturning due to the height of the shear force acting with respect to the soil interface. And then again, we have this note that reminds us that although the program allows us to define shears acting in both the X and the Z axes, it's going to keep those shears and those resulting moments separate, but track them along for us in parallel and report the results about each axis or in the direction of each axis independently, and there's no interaction between the shear in the X and the shear in the Z. Okay, so let's just come back to the vertical loads, and I'm going to just pop in some values. So let's just assume a 30 kip dead load and a 40 kip live load, and let's just leave it at that for concentrated vertical loads. And then for overburden, what we might say is that we have maybe a couple 100 pounds per square foot, so 0.2 KSF of dead load. For moments, I'll come over to the wind load condition, and I'll say that we have a moment that's acting about the Z axis, and let's just put in 24 foot kips. And then associated with that moment that acts about the Z axis will be a shear. So I'll come to the shear tab, and let's just call this a wind shear. And let's say that there is a shear of 8 kips at the base, and that would be in the X direction. So we've defined that as a Vx value. Okay, so that is a thorough look at the way that we would define the applied loads that are going to be resisted by the subject footing here on the Applied Loads tab. Obviously, you can use any combination of the load cases that are provided and any combination of the vertical loads with their overburdens, moments, and shears. Just keep in mind that they are to be entered as unfactored or service level loads, and then ultimately to be factored up when we move to the Load Combinations tab. So the Load Combinations tab is where we will move next. On the Load Combinations tab, we will select the load combination set that we want to serve as the basis for our combinations for analysis and design. And then we have a lot of control over the way that we can modify many of the details that go into those load combination sets. There's quite a bit of information here on this tab, so let's just take it in a nice slow progression all the way around and see everything that there is to see. To begin with, I'll start with this little white box which indicates ASCE 705. That tells us the currently selected load combination set. Now let's assume that instead of ASCE 705, I'd really like to use the load combinations from IBC 2009. So what I'll do is come over to this button called Change Load Combination Set, and I'll give that a click, and from the pop-up menu I will choose, in this case, IBC 2009. When I do that, it reflects IBC 2009 as the current load combination set, and all of the values now reflect those that are in the IBC 2009 load combination set template that's provided with the program. Let's just take a look over here to the left and notice that we have two sub-tabs. Service combinations, and as this note indicates, these are the combinations that will be used for the soil pressure determination. So notice that these are all at a service level. And then we have a tab called Factored Combinations. And these are the ones, as the note indicates, that will be used for concrete design, so for bending and for shear checks of the reinforced concrete section. Obviously, these are at a factored level. The next thing that I'd like to point out is that there's a little padlock icon over here. There are some instances where there needs to be some subtle modifications to the factors that come in from the selected load combination set template. So what you can do in those instances is click the padlock to toggle it to the unlocked state. Notice the change in the appearance of this table. And now you can come in and you can highlight these values and overwrite them with whatever value you see fit. So if you have a specific need to do something on a calculation basis, you can bring about that change by just editing the values right here on this template. And when you do it by using this unlock tool, this does not make changes retroactive to the template that's stored in the structural engineering library called IBC 2009. Instead, these edits will only be specific to this one particular general footing calculation. So they are truly a calculation specific edit. I don't have any need to make any particular changes, but I just wanted to point that out. So I'll just toggle this back to the locked state. The other thing that I'd like to point out is that there's an option to use the additional factors per the referenced section of ASCE 7. This is the tool that you can use to add that additional component of vertical load in the dead load category on the basis of the SDS value, and that would occur for all load combinations that include seismic in them. So that's the additional vertical load due to seismic. Notice that there's also an option to auto reverse the wind loads and or auto reverse the seismic loads. This gets at the fact that the wind comes and the wind goes, or that seismic shakes one way and then it shakes the other way. And so depending upon what your specific loads in the calculation are meant to represent, there are instances where it makes sense to run both the load combination that includes the positive form of wind or seismic, and also the load combination that includes the negative form of the wind or seismic. Just keep in mind that what this means is literally the algebraic negative of the wind and or the seismic. So if you have a situation where it is not meaningful to reverse the load by reversing the algebraic sign, then these probably aren't going to be of all that much help to you, and the way you'd want to account for that is probably to copy the calculation and just edit those loads that need to be handled in some sort of a different way. Okay, continuing around, notice that when we're looking at the service combinations tab, there is a column here called soil increase, and that right now it's populated with values of 1. In other words, no particular increase in the soil allowable bearing pressure, but there are times where the geotechnical engineer may give you the ability to increase the specified allowable soil bearing pressure by some factor for certain combinations, perhaps those that include wind and seismic. And so what you could do if you have a report like that is come in and just edit these values for the load combinations that include wind and seismic to reflect the increase that the geotechnical engineer has provided you. Continuing over to the left, we have a column of check marks. These are simply the indicator as to whether or not the combination should be run or not. So they're just toggles. You can check or deselect those. And then also at the head of the column is a run button with some common options. Mark all of them, clear all of them, invert the selections, or to just quit. The last thing that I'll point out here on the Service Combinations tab is that these descriptions for the load combinations take their cues from the load factors that are specified over here. So if you were to unlock these combinations and, for instance, specify a value of 1 in the earth pressure, notice that that just added the plus H designator to this combination. So those descriptions are intelligent and they reflect what is specified in the factors over here in the right-hand side of the table. If I come over to the Factored Combinations tab, everything is largely the same here. The run column is the same. The allowable soil bearing increase is gone, obviously, because the Factored Combinations tab has no reference to the soil bearing value. But notice that we can still unlock the combinations and edit the factors as need be. Also, we do still have the option to use the additional factors for the vertical component of seismic load and the ability to auto-reverse wind and seismic. The only other thing that's new or different on the factored combinations tab is that we have the option to indicate the nature of the live load that's represented in our model, because that dictates the value of the factor F1 that will be used on the live load in these combinations. Okay, so that is a very thorough look at everything that's on the load combinations tab. At this point, what we'll do is switch, and we will take a look at the results that are provided in the bottom half of the screen. We'll start with the calculations overall tab, and then take a look at each of the horizontal tabs that are provided in the calculations category. And then we'll wrap it all up by coming back and using some of the controls up here in the footing size and reinforcing category to actually make this footing work. We'll start out looking at the calculation results by looking at the horizontal tab here that's actually named results. Now when we look at this tab, we have a series of design checks or design items that are listed here. And then we have a status that's indicated by the leftmost column, where the X means that we have something that needs to be addressed and the green check mark means that everything is okay. Then we try to report what we refer to as a minimum ratio, although in some cases we can see that it's more of a text descriptor. So we'll take a look at those. And then we have both the applied and the capacity, or the allowable or permissible level, whether that's a pressure or an overturning moment or a sliding force or whatever. And then last we have an indication of the governing load combination that produced the controlling result. So if we just take a quick look down through the categories here, we can see that we have an issue with our soil bearing. Obviously we have a footing that's significantly undersized because the eccentricity is actually greater than half of the dimension of the footing itself, indicating that the resultant is outside of the footing completely. And that doesn't come as a complete surprise, because we did not go back and revisit the dimensions that I poked in as a starting point after we applied some arbitrary loads. So that's just simply a matter of not having gone through the first design iteration yet. Notice that we have an indication of overturning about the x-axis and about the z-axis. We only applied overturning loads, the shear and the moment, about one axis, so that's why we only see something meaningful about the z-axis. And then corresponding to that, when we look at sliding in the x direction and the z direction, notice that we only have non-zero values in the x direction. That's for the same reason that we only have moment about the z-axis, because we only applied forces that would cause sliding in the x direction. Then we have an uplift check, and I did not apply any loads that would tend to cause uplift, so that's what the program is indicating here. Now we get into our flexural checks, and when we look at flexure, what we have is a report of bending about the z-axis, but it's broken into two components: the bending that occurs on the positive x side of the pedestal and the bending that occurs on the negative x side of the pedestal, all for bending about the z. And then likewise, when we look at 90 degrees, we have bending that's about the x-axis, and we have a report of the result on both the positive z side of the pedestal and the negative z side of the pedestal, along with the applied load and the capacity and the controlling load combination. The next thing that we see is the result for the one-way shear check, and that occurs on all four sides of the pedestal. And then we see the result for the two-way or the punching shear check, and there's only one line for that, with its applied, capacity, and governing load combination. So again, we acknowledge that we have some work to do here on the basis of the red X's that we see here on the results tab. We'll put a separate item in the table of contents to come back and optimize the footing and eliminate those so that everything is a green check mark here. But that's a pretty thorough look at the results tab. The next thing that we'll take a look at in the calculations category is the soil pressures tab. Here on the soil pressures tab, I just want to point out that the note reminds us that the soil pressure results are based on the use of the service level loads. So that would be these service combinations that were defined, and specifically those that were selected to run. When we look at the actual values, I just want to compress the results and show that there are two sets of values. One for load conditions that tend to cause rotation about the z-axis, and one for load conditions that tend to cause rotation about the x-axis. So from there we can look down through, and on a load combination by load combination basis we can see the bearing load, the allowable bearing pressure, and then we have a resultant or a resultant eccentricity that's reported. So in situations where we have some moment being applied, we can actually see the value reported from the footing center line to the resultant, and they're broken up into dimensions that are measured parallel to the x, obviously for those forces that cause rotation about the z, and parallel to the z for conditions that would cause rotation about the x. Notice also that we have a couple indications in here of just pure instability, where the resultant is greater than L over 2. And again, we're aware of those at the present time. We know that our footing design is not complete, but we're just walking through at this stage to see what we're provided for results. Okay, continuing across, we have a category called soil pressures, and we report those soil pressures at four edges: the top and the bottom, the right and the left. So to try to identify one that might be somewhat meaningful, here we can see that we're rotating about the z-axis. If we were to jump back and take a look at our footing size, that would mean that we should see pressures, if we're rotating about the z, we should see pressures that are significant on the right and on the left, and that is in fact what we see, values non-zero on the right and on the left. At this point, if we picked a load combination that included some unbalanced load, like this wind moment, we can actually see that we have a condition where we have the higher pressure on the right, which is the positive x, which is exactly what the note told us would happen with positive moments and positive shears. And in this case, we have a soil bearing pressure value of 0 on the left hand side, which is the negative x edge. So that all is consistent with what we read about back when we were looking at the applied loads. The next column is called maximum, so that just extracts the maximum soil bearing pressure that was found to occur. And then the last column is a ratio of the actual to the allowable. So here again we know that with this preliminary footing size we have some highly overstressed conditions by a ratio of about 4 for this particular load combination. So that is everything that we see when we refer to the soil pressures tab. The next thing that we'll take a look at is the overturning and sliding stability tab. The overturning and sliding stability tab is broken up into separate sub-tabs that handle overturning and sliding, both of which remind us that they're based on service level loads. If we start with the overturning, we can see that we have two categories broken up by the two rotation axes. For overturning, in this particular example, rotation about the x-axis boils down to being pretty meaningless because we specifically didn't apply any overturning moments about the x-axis. So if I compress that, we can focus just on the z-axis, and here we can see that we do have a couple instances where we have a measurable overturning moment and a quantifiable resisting moment, and then what's referred to as an overturning ratio. Notice that we have a situation here where we have an overturning ratio that needs to be addressed. And again, that doesn't come as a surprise to us because we haven't optimized this footing yet. But here we can see exactly what is driving that overturning ratio based on the load combination that's causing those values. If we move over to the sliding results tab, here it makes sense that we won't have anything of interest when we look at sliding in the force direction of the z-axis because we didn't provide any forces to create sliding in the z-axis, but we do have some non-zero values of interest here for sliding parallel to the x-axis. So again, we see an indication of the sliding force, the resisting force, and then a calculated ratio as well. Notice that for each of these tabs, the sliding and the overturning, we can see a quick report of the minimum stability ratio. So if we had a more complicated situation where we had multiple load combinations that were causing sliding and or overturning, we could quickly just come over and take a look at the minimum ratio reported here on the far right hand side. So that's a look at the options and the results that are provided on the overturning and sliding stability tab. The next thing that we'll do, still in the calculations category, is we'll study the footing bending tab. Here on the footing bending tab, we're provided with a note that reminds us that the footing bending results will be reported with respect to the factored loads. So these are the concrete design load combinations that were specified. And the first piece of information that we're provided is the area of steel required parallel to the x direction or x-axis to address the bending about the z-axis, and the area perpendicular to that, the required area parallel to the z-axis to address bending about the x-axis. When we move down into the table, and I'll just compress the table data, we can see that we are again provided with results for bending about each axis independently. So taking a look at bending about the z-axis, we see an indication of the load combination, and notice that for each load combination there are two rows here. The reason for that is because as we move over in the table we can see a moment that's applied, and here is the reason for two rows, because we're reporting results on two different sides of the pedestal, on the negative x side of the pedestal and on the positive x side of the pedestal when we're looking at rotation or bending about the z-axis. The next column over tells us whether there is tension on the bottom of the footing, as in the case of a purely gravity-loaded footing, or if there might happen to be a situation like we can see indicated down here where there's actually tension developing on the top of the footing, such as if there was an uplift condition, or in this case we can see that one side is in tension on the bottom, one side is in tension on the top, so that's a footing that is under a moment and is causing enough net moment that we're actually going into tension on the top of the negative x side of the pedestal for this particular load combination. Continuing over, we can see an indication of the value of D, which is the depth to the rebar center line, the value of RU that's required. Next, we have a table that covers the minimum area of steel required based on a handful of different things. If we had selected the option to use ACI section 10.5 as the basis for our minimum steel, that's the 200 over Fy, or the new requirement that's 3 square root F prime C and some other info, we would see those values populated in this column. Since we did provide a 0.0018 ratio on the gross area of concrete for temperature and shrinkage, we see a constant value of 0.259 square inches of steel required in the temperature column. If we had chosen to specify a value that would be multiplied by the depth of the footing and the width, then we would see that requirement populated here. And then we also have a calculation of the required steel based on the applied moment, indicated in the applied MU column. So then what we do is summarize that by indicating which of those columns actually governs the required amount of steel. And for those that we can see here, it's actually the minimum temperature and shrinkage steel that governs. So then we summarize that by indicating steel bar area required, 0.259, and the area supplied, 0.88. So that's a quick check to see how we compare to what's required. We calculate and report phi-mn, the moment capacity, about the selected axis. And then last, we report a stress ratio so we can compare mu to phi-mn and see how we fare against that. If I was to scroll back over to the left, just remember that we've only been focusing on bending axis, bending about the z. You could also come up in here and expand the other category, which is bending about the x, and study all of those results as well. Okay, so that is a look at the footing bending tab and what it provides for us. From here, we'll move over to the last tab in the calculations category, which is called footing shear. The footing shear tab is a little interesting right now because it doesn't appear to be reporting any results for one-way shear. And I think the reason for that is because if we just come back and revisit the footing size and reinforcing tab and then take a look at the dimensions sub-tab, remember that we poked in some values here of about 3 feet by 3 feet, and the footing thickness is only 12 inches, so that would mean that there's really very, very little room for there to be any shear at all, any one-way shear, because once you add D to the face of the pedestal, you're actually outside of the footing. So what we need to do to make this a little bit more interesting is just bump this up to something like, say, 6 feet by 6 feet. Just a starting point, just a guess, but now at least we can take a look at some meaningful results here on the footing shear tab. Again, keeping in mind that we're going to have to go back through and optimize this and take a very close look at the reinforcing and so on. But what we can see now is that we have a list of concrete design load combinations, and for each of those combinations we can see a value for the one-way shear at the negative x and the positive x sides of the pedestal, and the positive z and negative z sides of the pedestal, and then the maximum factored shear reported, the allowable shear due to concrete strength, and then the ratio here, allowable strength to or applied shear to allowable shear. And then moving over, we can see the ratio for the two-way shear. Here is the, let me just click back one. Here is the applied shear for the punching shear check, the allowable value for the punching shear check, and now I'll jump over to the right and we can see the ratio for punching shear. So that's everything that we have to look at here on the footing shear tab, and that actually is the completion of all of the tabs that are here on the calculations category. So the next thing that we'll look at in terms of results is the sketch tab. Here on the sketch tab we can see a plan view of the footing with the coordinate axes superimposed. We can see a graphical representation of the pedestal in the proper location. The pedestal is dimensioned, the footing is dimensioned, the pedestal is located on the footing, and then you can even see an indication of the rebar in plan view as well. If we move over to the right, we can see two section views. There's an X x-axis section, so cutting through the footing and pedestal parallel to the x-axis looking toward the positive z direction, and then cutting through the footing and pedestal parallel to the z-axis looking in the positive x direction. And in both cases the bars are indicated. So that is a complete look at the sketch tab, and that brings us to the end of the results that are provided. The last thing that we'll do is we'll take a look at improving the design to try to get an efficient design and one where we are assured that all of the checks pass here on the results tab. Now, when it comes to trying to optimize this footing design, we happen to have a situation right now where all of the checks are showing green, and that's simply because I arbitrarily came back in here when we were looking at footing shear and I bumped up the footing size to something that was large enough that would produce a meaningful one-way shear value. But there's really no guarantee that what I've done here is an efficient design. So this is a great place for us to use the Auto Calculate Footing Size and Thickness button, and I am on the Dimensions sub-tab of the Footing Size and Reinforcing tab for reference. So what we can do is click this button, and it offers us a couple different options, either to keep the footing square or to allow it to go rectangular. Let's just assume that we want to stick to square footings for convenience. So I've clicked the square footing option. And now, and actually let me just revisit that one more time. It's important to understand what this function is doing and what it's not doing. What it can do for us is it can determine the dimensions that are required to satisfy the soil bearing pressure and the overturning checks, and it can determine the thickness of the footing that's necessary to satisfy the one-way and two-way shear checks. But what it cannot do is determine the thickness of the footing that's required to satisfy the flexure checks, nor can it actually design the reinforcing for us. So consider this to be a geometrical aid in determining the plan area and to some extent at least the minimum footing thickness that's required to satisfy punching shear and one-way shear, but then just understand that it's going to require some additional work on our part to come in and finalize the design. Now, it took a square footing that was 6 by 6, and it has optimized that down to something that's 5 3/4 by 5 3/4, and we can see by looking at the soil bearing ratio that it's pretty close to 1. So it has done a pretty efficient job of finding a square footing size that works. And if we look down through at the one-way shear and the punching shear checks, it has found something that works at 12 inches thick. Now, we may not feel comfortable working with something quite that thin, but let's just bump this up and say that we had a company standard of nothing less than, say, an 18-inch thick footing. Okay, so by doing that, what that has done is it has increased the soil bearing pressure somewhat because of the weight of the concrete, and so we may actually just end up right back at the 6 by 6 footing that we originally had. Okay, so we're there. Everything looks good on the check marks, so that's a good sign. But then what we can do is come back and just revisit the reinforcing. Again, a couple different ways we can do this. Remember that when we were on the footing bending tab, we saw a report of the area of steel that was required. It was 2.33 square inches for the current design conditions. So what we could do is we could come in and use these rebar lists, and we could say that we don't want to use anything less than a number 5, and we don't want to use anything greater than, say, a number 8, and for a 6 by 6 footing we don't really want to use anything more than about, say, 6 bars. So what we could do then is scroll down through this list and look for some combination of bars that would provide 2.33 square inches. We could go with 4 number 7 bars, or maybe we'd prefer to use more bars of a slightly smaller size. So we could take a look at limiting the ending bar size to say a number 6. Okay, so 6 number 6s will do the trick, and actually it just looks like we happen to be at a good reinforcing pattern right now. The 6 number 6s that we originally guessed just happen to be pretty functional for this design. So in a sense, I was hoping to find something that would give us a little bit more of a hassle here so that we could fight a little bit to try to find a pattern that worked, but I think the idea is demonstrated fairly well, that you can play with the number of bars and the size of the bars that are required. If you're trying to match an existing footing schedule, you can just set those and check to see if your existing rebar pattern works. If you're just doing a one-off footing and you want to try to get to the answer quicker, this rebar selection utility can be really helpful and very handy at trying to optimize the footing. So at this point we have something that works for us for all of our checks, and we would probably say that this footing is ready to be printed and studied in detail just to make sure that all of the details are provided and that we're satisfied with the design. Now there's one final topic that I'd like to cover in the general footing video, and that is a very common question with this module, and it relates to the reinforcing, specifically the use of top mats in footings. If we come back to the footing size and reinforcing tab, reinforcing sub-tab, notice that there's only one location where we can define the rebar mat. This does not make reference to it being a bottom mat or a top mat. It's just a definition for a mat. And there's one location where we enter a value for the clear cover. It does reference the bottom because most commonly the mats are provided at the bottom, but we can think of this as the rebar center to concrete edge at either the top or the bottom. What's important to understand is that when we get the footing generally proportioned correctly and we get in the neighborhood of a final design, we need to come to this footing bending tab, and for our purposes we didn't have any bending about the x-axis, but we did have bending about the z-axis, and we need to skim down through this tension at bottom or top column, and we need to look for instances where there is measurable tension at the top. We definitely have some of those instances in the current design. This is an indicator to us that this is a footing that requires a top mat. If we only saw bottom tension everywhere for all of the loading conditions on the bending tab, then that would be a footing that would not require a top mat. But that's not the case for our example. This one definitely does call for reinforcing at the top, and you can rest assured that the proper moment is being evaluated here. In this case, it looks like it's not very significant for that particular, in fact for most of these. Here's one where there's a small measurable moment in the top, but nonetheless in certain instances you'll see that there's a significant design moment to be dealt with on the top, producing tension in the top surface. So in the present implementation of the module, it is assumed that the defined mat will automatically be provided by the designer in the top in situations where the footing experiences tension in the top. And that's fine as long as you understand that you need to look down through this list and determine whether top reinforcing is required. There's one other small detail to consider, and that is back on the General tab where we specified the minimum steel ratio for temperature and shrinkage. What we provided was the 0.0018 value that's common for footings. And the way that the module is currently implemented, it calculates that 0.0018 value and it requires that in this column here, and it it doesn't actually take into consideration whether there is a top mat or not. So what ends up happening is that in the current implementation, any mat will be held to this entire value. Now, if you only have bottom reinforcing, that works out fine because all of your temperature and shrinkage requirement has to be met by your bottom mat. But if you're in a situation where you do have both top mats and a bottom mat, then what you might do in the current implementation is just use 1/2 of the 0.0018 value, with the understanding that you'll provide half of the total in the bottom mat and half of the total in the top mat. And in that way, you'll get an accurate representation of the minimum amount of steel that's required in each mat in this column headed temperature and shrinkage. And when you provide your details and your drawings and you call for both a top and a bottom mat, you'll know that you're effectively doubling the 0.0009 value that could be typed in here and satisfying the 0.0018 that's actually required for code. So I just wanted to include that because it is a common question. We're looking at ways to try to make that even a little bit more useful and a little bit more friendly. But at present, this is the way that we handle that condition with the minimum steel requirement for temperature and shrinkage. Okay, the last thing that I'd like to point out is that if you're in the mode of output, keep in mind that your tools are provided right up here. You have the ability to control what is included in your output, and that was from the Properties button. And then, as usual with the rest of the structural engineering library, you can preview the print before you actually commit to printing it, and then from there you would have the option to print it to the printer or print it to PDF. If you've made some changes and you know you're happy with it, you can just use this icon to print directly to a PDF, or you can use this icon to print directly to your printer. So that's a wrap up on a thorough look at the general footing module. I hope that it's been helpful. Thanks very much for your time. Take care and have a great day.